podcast. This is Mr. White.
Mr. Johnson.
And today we're going to talk about energy conservation as it relates to your investigation. So we wrote down some equations last time. We talked about delta E equals 0, where delta means what?
The difference of energy.
Right, so the change in or difference of, E of course is energy, and according to energy conservation, the difference of or the change in has to be
0.
0. There is no change. It means conservation means that it stays the same.
Correct.
I'm a big fan of writing out EI as EF. Big fan of that. Where we're talking about the initial energy equaling the final energy. Okay. So let's relate that directly to the activity. And so we saw some videos of a figure skater and a guy dunking a basketball, but then we actually did something.
Right.
And so I want to talk about what we did.
We actually did it as one person. We had one basketball player in the class, so they actually demonstrated, and I measured using the meter stick with their center of gravity.
Okay. And so we measured, the first thing was how much knee bend there was, right? And so what does that tell us?
Well, that's the elastic potential energy because they haven't actually jumped yet, but they're getting ready to. It's kind of like when you took the ruler and you bent it down with a penny.
Ooh, I like that. Now that gets tricky because we don't really know the spring constant of our muscles.
Correct.
So is there another, I like that it is exactly how much we are stretching those muscles. But is there another way to approach this? Maybe through work.
Okay. Well, that's what they had to do. So.
Okay. Yeah, they had to do work to jump up into the air. So in the next moment in time, back to my normal awful drawings, they're on their way up. Okay. So they have some speed. And so we're assuming they've just left the ground. What kind of energy do they have at that moment?
Kinetic.
They have kinetic energy. So V, therefore, kinetic energy. Then this guy must be Michael Jordan. He's really high off the ground. He has some height, which means that he has gravitational potential energy.
Right.
And then he is on his way back down, so he has some downward speed. And what kind of energy does he have now?
Well, it'd still be kinetic.
Still coming back to kinetic.
He's moving.
And then in the last shot here, when you land, you tend to bend at the knees because you don't like to be hurt.
No.
So the ground is doing work on you. So we come back to this. In order to do work, you have to apply a force over some distance.
Correct.
That distance happens to be how much you bend.
Right.
Okay? And that force happens to be equal but opposite to your
Regular.
to your weight, right? Because that's what you're overcoming.
Now, are we saying weight or are we talking mass? 'Cause I know,
Well,
those two words, they're not really interchangeable.
So since it's a force, it's a great question, by the way. We have to go with weight because it is a force. Now, when we talk about the kinetic energy, which is what my jumper has as he is leaving the ground, right? His work is being converted into kinetic energy. Then we're talking about half his mass times his speed squared.
All right.
Okay? So he has this kinetic energy because he has just left the ground. His muscles have released the work and given him kinetic energy. Okay, so step 1, step 2. Step 3, he's got a maximum height, a gravitational potential energy, which is his mass times the acceleration of gravity times his height.
Mm-hmm.
Didn't we measure height? Isn't that what we were measuring for, or one of the things we were measuring for in the investigation?
Right, to see how high, like you were supposed to put a piece of tape on your hip, and you wanted to see how high when they jumped that the piece of tape got, and you measured that.
Right. So that gravitational energy, of course, is equal to the kinetic energy he had right before or right after he left the ground. It's also equal to the kinetic energy he has right before he lands. Same equation. So if you knew all of this, and by the way, we had you find your mass, we wrote gravity out, you measured the height, you can do some math and figure out how fast you're going right before you hit the ground and right when you leave the ground. And if you know the bending distance, okay, so, you were standing like this, X marks the spot, well, that spot has changed by some distance. You can go back and figure out the push force. And you can come back here and you can do the same thing. Look, the work is still the force times the distance. And the distance is how much I bent, so how much force is done to you. So the amount of work that you have to do to land should be equal to
The amount of work that you need to take off.
That's it, right? And it should be equal to how much gravitational potential energy that you had, or how much kinetic energy you had. Now, there's a lot of points in between where you had both KE and GPE. But when we add those up, they should equal
0.
not 0. They should equal how much we had, right?
Oh, you're not talking about overall.
Overall,
Yeah.
it should equal to how much we had at the beginning, every point in the middle, and at the end.
Right.
The difference in them should be 0.
Okay.
Yeah. Okay. So then we have this stopping distance. So, hey, when we talked about this, when you land after you jump, you bend your knees, right?
Correct.
What if you didn't bend your knees? How would that feel?
It would hurt.
That
Well,
would-
well, it depends on how hard you actually jumped, I would think.
So let's say I were to step off of one of the tables in my room and land without trying to bend my knees. How's that going to go for me?
Yeah, I think you'd be okay on that distance.
Would I be in pain?
Maybe.
I'm going to say I'm going to be in pain.
I don't know. You're pretty fit.
I've done this.
Oh,
It hurts.
okay.
So what happens here is I had gravitational energy at the top of the table. I gave myself kinetic. The ground does work on me to stop me.
Right.
Okay. Do I have a big or a small stopping distance when I do that?
I would think it'd be a smaller stopping distance.
Because I haven't bent my knees.
Right. So
So what has to be true of my stopping force?
it's got to be greater.
Yeah. So when you land, and as a coach, I never thought about this stuff when I was an athlete, but now I'm a science teacher and a coach, and I think about all this stuff. They tell you to do things like follow through, or to bend your knees, or to keep your back straight. It all has physics applications. So by increasing my stopping distance, I decrease my force because I still have to do the same amount of work
Right.
no matter what. If I choose not to do this, okay, the work will be the same if I have an enormous force and a very tiny stopping distance, except here we get injured. Here we stay safe.
You might have just had some athletes want to quit since they think they're doing physics now because they don't like physics.
Well, they're doing physics every time they're in the weight room and every time they're on the floor, on the field. My water polo players do physics. I actually bring it up. Physics, this and that, and they kind of roll their eyes, but they don't have a choice. I talk about it in swim practice too. Physics, lots of physics in swimming. Lots of physics everywhere. So that wraps up Chapter 2 and the physics in action, the sports and physics worlds collide. So signing off, this is Mr. White.
And Mr. Johnson.